Okay, good afternoon, class, and welcome Lex, Lanisha, Nigel, Lex, Marley. Okay, Keston, Kendra, Kaylin. Okay, I think we're all here. Let's see, 1, 2, 3, 4, 5, 6, 7. Okay, all right. Let's see. No, Monnier is not here yet. Okay, go ahead and sign in so you can get your extra credit points, and we will begin. I have um, I have some material I want to cover today, but before I do that, I want you to go ahead and assemble the items that I sent to you, even if you can just make sure they're open on your desktop or open on your laptop, or if you printed it out, that's good. So today, class, we're going to conclude our lecture with chapters 14 and 16. And what I have sent to you already is just a very brief introduction of what I want you to know about these chapters. As you can see, there is quite a bit of material that you are to be familiar with from these 16 chapters. And of course, we've only touched the surface of much of it. I only consider myself as having introduced you to some of these topics. But if you are in need of further exploration and further understanding with your textbook, hopefully with your textbook and what I have given you, you will be able to delve much deeper and have an opportunity on your own or in different class to really explore our physics. So what I have given you also is a compilation of equations or quizzes or statements or just something to carry you through what was the objective of this course. So with that in mind, please pull out the final equation quiz, and let's look at beginning with number 112. Now, this final equation quiz, I encourage you to have filled out. Tomorrow in class, I will make sure that if you have any questions on anything on this sheet that you don't understand, that I will give that to you. So this sheet you're going to have available in front of you during the final exam. The final exam is comprehensive. It would include chapters 1 through 16, omitting the ones that we omitted. I think we omitted 9, 10, and 15. So all the other chapters will be on the exam. Not only will you have problems to solve, you will have concept questions, you will have true and false questions, and you will have fill in the blank questions as well as the problems. So the exam will pretty much cover some of the basic materials that you should have learned. Now, so that you won't be fearful and thinking that you have to know all of this, if you can just demonstrate that you have learned something. When I say something, that means that it is not, nothing is written in concrete. In other words, after I grade the exam and I've given, say, 100 questions, and the class is averaging around, well, I'll say that the highest score I saw was 65. Now, someone asked me, do I grade on a scale? Well, I don't grade on a scale, but what I'm trying to say is if the highest person in the class has a 65, and I figured that I gave enough questions that a 65 would be included, would be considered an A, that would be an A. And then, of course, a 55 could be a B, a 45 could be a C. Those are just random numbers. Now, I'm not saying that because someone could get 100. And then, of course, that would mean that I taught enough material well enough that one person actually earned an A out of what we call a true A. And then that would mean that in the 80s would be a B, and the 70s would be a C. But normally with the kind of final exam I give, 100 is not possible because I'm not expecting you to know everything. And in fact, if you come across a topic and you don't understand it well and you skip it, it will not affect your grade if you do well in another area. I've seen that some students do very well sometimes on these last chapters because of the simplicity of the equations and the simplicity of the concepts than they do on the earlier chapters. So say, for example, chapter 5 was difficult for you, or chapter 8, but chapters 14 and 16 are relatively simple. So those problems you answer well, and you can demonstrate you understand about the gas laws and about waves. That being the case, your overall score can still be an A, even if you don't understand every concept. So what does that mean then? This time next week, next Wednesday, you will be taking the final exam. So now you have an entire week to go through your final equation quiz and determine what it is you don't understand so that we can spend time in class or one-on-one sessions reviewing that material. Okay, that being said, then let's go to number 112 in the handout. Now, class, I took a lot of time to try to prepare this for you, and I'm hoping that you will see the value of it. I do this with every class all the time. So this is my way of providing you with a study guide. And I try to begin at the first chapter and work my way through to the end. Already on the 112, I have the ideal gas law. Now, let me explain to you what that means, okay? Before I do that, though, the author begins with the kinetic theory and how we're going to discuss that. So he begins that with talking about molecules. So listen to this, what he says. You have your textbook. I'm on page 380. Often, we wish to compare the mass of one atom with another. To facilitate the comparison, a mass scale known as the atomic mass scale has been established. To set up this scale, a reference value, along with the unit, is chosen for one of the elements. This is our reference element. The unit is called the atomic mass unit, and we use the symbol U. By international agreement, the reference element is chosen to be the most abundant type of isotope of carbon, which is called carbon-12. Its atomic mass is defined to be exactly 12 atomic mass units, or 12U. So we're going to talk about first, what is the atomic mass unit and where did that come from? So before I go further, let's go back up to one of our constants, which is a unit. So I want to say, that's why I put this up here with let me see, where did I put atomic mass unit? Did I move it back down? Let me see where I put it. Okay, I thought I put the atomic mass unit at the beginning. Hold on, let me see where I put it. Let me look for it, hold on. Oh, there it is, number 15, okay, 15. So one atomic mass unit. So we just use the symbol 1U. So right here, one atomic mass unit. So that's just simply one, hold on. Okay, 1U. Okay, 1 atomic mass unit. Now, what we know is that this mass is the unit of mass in the atomic mass unit scale. Now, before I finish filling that out, I want you to look at the periodic table that I gave to you. I sent you a periodic table. And on that table, for example, you see the element hydrogen. And you see the numbers 1.00794 underneath that. That's because that is the mass of one hydrogen atom in the unit of atomic mass units. Now, what is that mass in terms of our unit for mass? And we know that we measure mass in kilograms. So you can imagine that this must be a very, very, very small number if I convert it into kilograms, and it is. So here I want you to write that 1U is 1.6605 times 10 to the minus 20. Oops. I don't know what happened. Hold on, class. Stuff is silly. Uh-oh, hold on. Okay, hold on, class. Let me close this. Maybe this is messing me up. Let me close this thing. Okay, let's see if I can get this stay right here. Okay. Minus 27 kilograms. So I meant to put that in the conversion section up here at the top, but that's okay. I have it down here still. So what's this number now? This is the unit, the atomic mass unit, and we simply use the symbol U. Now, if you look at carbon, you may see 12 I think it's 12.011. That's because even though we say it's exactly 12, they still include in that the average, which has a little bit of carbon 13. But for our purposes, we're going to just say that the atomic mass unit for carbon is 12. Okay, now, the molecular mass of a molecule is the sum of the atomic masses of its atoms. For instance, think about water. So we know that water is H2O. That means I have 2 atoms of hydrogen plus 1 atom of what? Oxygen. And I have that mass. And when I add those together, I will get the atomic mass unit, the mass of hydrogen plus, the mass of oxygen, the mass of water, which is H2O, which is 2 hydrogen atoms and 1 oxygen atom added together. So hydrogen we see is 1, and oxygen is 15.99. Let's just say 16 for all practical purposes. So we got 2 times 1, which is 2, plus 16 is 18. So that's 18 atomic mass units. That is the atomic mass of what? Water. Now, macroscopic. Now we know that atoms is on the microscopic, atomic level actually. So let's talk about this on the macroscopic. Macroscopic amounts of materials contain large numbers of atoms or molecules. For example, this is a water molecule. A water molecule is composed of atoms. So this is a molecule. It comes together as a molecule. Even in a small volume of gas, like 1 cubic meter, okay, a meter by meter by meter, 1 cubic meter, for example, this number is enormous. It is convenient to express such large numbers in terms of a single unit called the gram mole, or simply the mole. I'm not going to spend a lot of time on this, just to remind you that you have heard of the mole, I'm sure, in your chemistry classes. Okay, so 1 mole or 1 gram mole of a substance contains as many particles, those particles are atoms or molecules, as there are atoms in 12 grams of the isotope carbon-12. Now, what is that number? Well, you may have heard that number before. It's called Avogadro's number. You've seen it before, I'm sure, in chemistry. And that number is called Avogadro's number. So I'm sure you've heard this number. Watch this number. It's going to be familiar to most of you. 6.02 times 10 to the what? 23rd. That's Avogadro's number. So that means if I had a mole of anything, 1 mole, I would have this number of particles, particles being atoms or molecules, Avogadro's number. So, thus the number of moles N contained in any sample is the number of particles N in the sample divided by the number of particles per mole, which is Avogadro's number. Although defined in terms of carbon atoms, the concept of a mole can be applied to any collection of objects by noting that 1 mole contains Avogadro's number of objects. So, thus, 1 mole of atomic sulfur contains 6.02 times 10 to the 23rd sulfur atoms. 1 mole of water contains 6.022 times 10 to the 23rd water molecules. 1 mole of golf balls contains 6.02 times 10 to the 23rd golf balls. The mole is the SI base unit for expressing the amount of a substance. So please understand that when you have the value of the numbers on your periodic table, that number is the mass in atomic mass units. So to convert that into the SI unit, we have to use this conversion. We also know that Avogadro's number is the number of particles we have if we have 1 mole of whatever it is. Okay, hope that's clear. Now that's basically all we're going to talk about from that part of the chapter, the molecules. Now let's move to the second part of the chapter. Second part of the chapter is the gas laws. And I'm going to break that down for you as simply as I can. So by doing that, before I write all this down, I want to tell you that the ideal gas law, PV equals nRT. Now, if you look in your textbook, I'm on page 383. An ideal gas is an idealized model for real gases that have sufficiently low densities. And we know that density simply means mass per unit volume. So an ideal gas will have a very small a very small mass per unit volume. Okay, because it has a very low density. All right, now let's go over to our first expression for the ideal gas law. So the ideal gas law, we write it as PV equals nRT. P stands for pressure. V stands for volume. T stands for temperature. N stands for the number of moles. And R is going to be the universal gas constant. Now, on this page, I did not give you the universal gas constant because we don't ever use it for right now. If you wanted to know what it is, it's a constant, which means its value is fixed, 8.31, and it's joules per mole degree Kelvin. So the first thing you notice is that in the gas laws, the unit for temperature has to be in Kelvin. Okay. Now I'm going to go to the whiteboard and show you these equations. Okay. Okay. So the first equation I gave you was pressure times volume is nRT. So that means that pressure times volume divided by T is equal to N times R. Now, N, we say it's the number of moles in a gas, which will remain constant if we're not putting in more gas or less gas, right? It will remain constant. And then, of course, R is the universal gas constant. It doesn't change. So this is really constant. So that means that I can write the ideal gas law in terms of what happens or what changes when I change the temperature, pressure, or volume. So one way to think about that is P initial times volume initial over temperature initial is equal to a constant. So when I change it, it's going to be my new pressure, P final, my new volume, V final, over my new temperature, T final. So that's one way to write the gas laws. And this is another way to write the gas laws. Because I'm telling you, once I modify the pressure, volume, or temperature, what results is constant. And so that means it remains the same. The pressure, the product of these remain the same. In other words, the value, whatever this is, it's constant. You may have seen this written, P1 V1 over T1 is P2 V2 over T2 is P3 V3 over T3, which is Pn Vn over Tn, which means that the value of that number has to remain constant. Now, this is, of course, true for what? Ideal gases, okay? It has to be an ideal gas. Now, with that in mind, I can easily show you how we derive the other gases. Look at this. What if I'm modifying these gases in a way where first I decide to keep the temperature constant? In other words, T initial and T final are the same. And when that's the case, of course, when they're the same, they don't change, then I can cancel that out on both sides. And that means that when I keep them constant, P1 V1 equals P2 V2. What does that mean? Well, first of all, we call this Boyle's law, B-O-Y-L-E, Boyle's law. Now I'm going to show you that on a picture. Okay, so look at my picture here. This is my first picture. This is Boyle's law. Look what happens. already I have said that I'm keeping the temperature constant. So in this picture, I have a 100 kilopascals. This is my pressure. Pressure means I'm forcing down. When I force down on this gas, this ideal gas, of course, you know the volume is going to do what? It's going to decrease. I'm adding pressure. In fact, I've gone from 100 kilopascals to 200. So my pressure has increased. And what happened? My volume had to what? Decrease. But not only that, if you notice very carefully, it has to decrease proportionately. In other words, when I doubled the pressure from 100 to 200, the volume had to decrease by half. The volume was 1 cubic meter, and now it's 0.5 cubic meters. So I was hoping that this picture would help you to see that what happens in Boyle's law, it says that it is inversely proportional. Okay, so Boyle's law is inversely proportional. I want you to remember that when we solve the problems in just a few minutes. It simply means this. If the pressure goes up, the volume goes down by the same proportion, inversely, okay? So that means that when I double the pressure, I halfen what? The volume. Or how about here? In this case, the pressure increased by 10 times. You see, 100 kilopascals up to 1,000 kilopascals. That means that my volume had to decrease by what? A factor of 10, because 100 times 10 gives me 1,000. So this number has to go down by what? A factor of 10. So rather than having 1 cubic meter, I have what? A tenth of a cubic meter. That's what it means. That's Boyle's law. Okay. Now, what happens when I keep the I can keep the volume, temperature constant, or I can keep the volume constant, or I can keep the pressure constant. It depends on which one I want to keep constant, and it doesn't really matter. So in the next case, let's just say I want to keep the pressure constant. That means that in this picture up here, okay, I'm gonna write it again. P1 V1 over T1 is equal to P2 V2 over T2. But in this case, I'm going to keep the pressure constant. That simply means that the pressure is the same. I'm not adjusting the pressure at all. So what happens then? The pressures will cancel out. So now I have an equation that says V1 over T1 is V2 over T2. Now, let me show you a picture. Okay, the first thing you notice here in this picture is that I cannot put my temperature on the Celsius scale, because if T1 was 0, I cannot divide by 0. So the first thing you want to see, even in this equation, is that the temperature cannot be in the Celsius. The temperature has to be on the absolute scale. Now, this is called Charles' law. I think it's Charles with the S. Charles law. And it simply says, if I keep my pressure constant, then when temperature goes up, volume goes up. In other words, in the case of Charles law, these are directly proportional. Okay, so let's see a picture of that. In some cases, a picture is worth 1,000 words. So look what happens here. I have my volume. My volume is 1 cubic meter. My temperature is at 0 degrees Celsius, which I must convert into what? Temperature Kelvin. So in this frame now, this represents my pressure, okay? So you say, okay, but in this case right here, the volume has what happened to this volume? It has what, class? It has decreased, right? It was 1 cubic meter, and now it's what? It's a half of a cubic meter. So what happened to my temperature? My second temperature did what? It also what? Went down by half. How about right here? What happened right here? Okay, right here, if you notice now that my temperature has doubled. It was 273. I doubled the temperature, and what happened? My volume doubled. So when I halfen it, it halvens. When I double it, it doubles. So in Charles' law, following the ideal gas, it will be what we call directly proportional. As the temperature increases, the volume also increases by what? By that same amount. That's called Charles' law. Okay, so let's go back to our laws. So we said for Boyle's law, I can't write it in there well, so I'm gonna write it here. Okay, my pen won't come up, but you have it on the picture. You have it on the okay. So this is Boyle's law, and this is Charles' law. And those are the two laws that we're going to discuss. Oh, it's 203 from chapter 14. Okay, let me move to the handout that I gave you very quickly. Okay, so this is the handout for chapter 14. So here we have just some, I call them concept questions, but they also have a little bit of math for you to work out. And let me just show you one in chapter about the gas laws. Let's look at one like number 11 very quickly. Okay, an ideal gas at 0 degrees Celsius is contained within a rigid vessel. So if the vessel is rigid, that would mean that the amount of it, okay, the number of molecules and all that are the same. So what you want to do in a problem like this, class, you want to just think about, oops, hold on. Okay, you want to just think about it by first writing out your gas law. Okay, okay, my pencil's not writing right now. I don't know what's happening. Okay, there we go. Okay, so what we're saying then is that in this problem, helium gas is 20 degrees Celsius. So my temperature initial is 20 degrees Celsius. Is confined within a rigid vessel. The gas is then heated until its pressure. So you see, I didn't give you a problem with pressure, um, but I'm going to show you this until its pressure is double. So that means that first I have my initial pressure. I call that pressure initial. And then I have my final pressure. I don't know what it is. I just know that it has doubled from the initial. So I just say 2 times the pressure initial. And the question is, what is the final temperature of the gas? So the way you have to solve this problem is you have to put in the units, what? The units have to be what, class? The units have to be on the Kelvin scale. So you can't put in 20 degrees, but you can put in what? 293 degree what? I'm sorry, you can't put a degree symbol. Ooh, almost messed up myself. When we do Kelvin, if you notice, we don't put the degree symbol. So I put in what? 293 degrees. Okay, make sure you do that. If you don't do that, then the problem will not come out correctly. Okay. Now, let's look at one like number 10, and I'll show you another example. Okay, so a sample of a monatomic ideal gas is originally at, okay, T is in what? Celsius. So we have to put in what? That plus 273. So we're going to say 293 Kelvin. What is the final temperature of the gas if the pressure is doubled? Again, now the pressure is doubled, which means that first I had P initial, which was P initial, and now I have P final, which is 2 times P initial. And what it says now, and the volume is reduced, which means that first I had V initial, which was V initial. And now I have what? Now I have volume is reduced to 1/4 its initial value. So that means that my volume final is my initial over what? Over 4. So these are the type questions that you're going to be answering. And you have to do them making sure that you put it in what? The Kelvin scale. Even though you give it to you in Celsius, make sure you can put the given down here that it's in Celsius. And once you do that, you're going to simply be solving the problem that says P initial, V initial divided by T initial is P final times V final divided by T final. That's the equation you're going to be solving. You shouldn't have any difficulty on that. Okay. Let me go now quickly to the next section, because tomorrow I want to make sure that we work on these problems as well as begin our review. Okay. Our last set of equations has to do with wave speed. So by wave, I don't have time to go through the entire chapter, but we're going to think of, I'm not sure what's going on. I'm going to just go to the whiteboard and you can just copy it on your paper later. Okay. So by wave, we simply mean a sinusoidal pattern, which you have seen. Okay. I got it on the assignment too. Okay. We have a wave from beginning of the wave to the end of the wave. That's the wavelength. Now this wave is propagating. It's propagating through space, or it's propagating through material even, because we have what? We have longitudinal waves, we have electromagnetic waves, we have transverse waves. So all these just waves. And when we think of a wave, this is a pattern that we see in our I guess as our convention. So what I want to show you now is in the assignment that I gave you first. Let me go to the assignment, the handout that I gave you right here. Let me share this. Okay, so let's look at number 2. The wavelength of the wave shown in the figure. So I said the wavelength is from where the wave starts to where the wave ends. That's my wave. That's my wave. This is my wave. This is my wavelength. So this is my wave moving through space. This is supposed to demonstrate a wave that's propagating along this axis. And it has wavelength from here to here. It has an amplitude. The amplitude goes from the axis to the highest point, or from the axis to the lowest point. That is called the amplitude. But for our purposes, we want to talk about what is happening when this wave is moving through space, moving through the material. All right, now go back to my board. So the first thing we talk about is the wave speed. The wave speed, we know we use symbol V for speed. The wave speed is equal to the wave length times its frequency. Its frequency is how often it passes a certain point. How often it passes that point is its frequency. So the wave speed is the wavelength times frequency. For wavelength, we use the symbol lambda. Okay, and we know that length is measured in meters. For frequency, we're saying how many move past a certain point per second. So for frequency, we say how many, the number per second. So therefore, we get our units are meters per second, which is the same unit that we had before for speed. Speed is always in what? Meters per second. Now, what is this frequency? The frequency is how often it passes this cycle. How many pass this cycle per second? How many pass this space in a unit of time? That's its frequency. So the inverse of the frequency is the time it takes to go past that point. So the period, we call it, which is like the time it takes to go past, the time is the inverse of the frequency. So therefore, we know that we have 1 over 1 per second. 1 over 1 per second would just be what? Seconds. So the time, which is the period, okay, we call this the period, is just in seconds. Now, what's the name for this per second? Because we didn't give this a name. So when the frequency is defined as 1 over the second, we give that name the hertz. And you probably have heard of this. Listen to radio, you've heard of megahertz, you've heard of well, mostly megahertz. All right, on the radio. So this is the unit for frequency. So from there, you can go and put in your equations. In other words, if I wanted to find the wave length, I would say the wavelength is the wave speed divided by the frequency. Or I can say the frequency is the wave speed divided by the wavelength. We'll get the frequency, which also now we know is what? 1 over what? The period. So all these equations now just are simple, basic equations that talk about the basic wave. Now, I want to throw in, just sort of quickly here, what we call the electromagnetic wave. And the only key thing for the electromagnetic wave that I want you to know is that the speed is always the speed of light, which is 3 times 10 to the 8th meters per second, the speed of light. So let's just talk about that quickly, and we'll be ending this equation quiz. So tomorrow in class, what I'm going to do is begin going through these equations, making sure that you understand how these equations are to be discussed, how they are to be understood in our lecture, in this course. I'm trying to feel why my pen won't write. Hold on. I don't know why it won't write, but oh, there it is. Okay. So we said we want to find the frequency. We said the frequency from this equation would be what? The wave speed divided by the wavelength. So wave speed, we said, is in meters per second. The frequency, if we solve this equation for frequency, we have the wave speed, which is meters per second. And we're going to divide that by what? By lambda, which is meters. So meters and meters will cancel out. We get 1 over a second, and we call that the hertz. So the wave frequency unit is the hertz, but the hertz means what? A per second. Then, of course, the wavelength, which is lambda, we said is the wave speed divided by the frequency, and that, of course, is in meters. And then the wave period, T stands for period, is 1 over the frequency, and of course, that unit would be what? The seconds. So, hopefully, we have our equations. For Boyle's law, we said that P1 times V1 is P2 times V2, keeping what? Temperature constant. And in Charles' law, keeping the pressure constant, we said V1 divided by T1 is V2 divided by T2. Up here, we said that these are inversely proportional. And here we said that they're what? Directly proportional, but the temperature has to be on the what? On the Kelvin scale. Then the gram mole or the mole, how do we define that? Okay, the mole is what? You have to have what? If we have Avogadro's number of it, of that particular substance or atoms or molecules, then we would have exactly Avogadro's number if we have what? A mole of it. Okay, so with that being done, class, I have finished everything that I wanted to cover in this chapter as far as on this page. Now, 2 other items I sent to you. I want to show you that real quickly. I mentioned the electromagnetic wave, okay? The electromagnetic wave is a wave that moves at the speed of light. And all of these are considered, all of these are the electromagnetic waves that we are familiar with, beginning with radio waves, okay, with a low frequency, all the way up to gamma rays, which have a very, very high frequency. Or how about wavelength? As you can see, gamma rays have a very, very, very tiny, tiny, tiny what? Wavelength compared to radio waves, which are long waves, 10 to the fifth. So you can see now how that equation actually works, how they are sort of inverse of each other as far as the magnitude of them. Now, this small sliver right here, this small sliver is what we call visible light. Because we get our light from the sun, our eyes are such that we can only see in the visible light region. That's where the human eye can see. And of that, it's most sensitive in a certain range. And that's the problem I've given you on your assignment. In fact, let's look at that problem. Now, the main thing I want you to notice here is something you probably had in high school called Roy G. Biv. You see it right here. Roy, red, right? R-O-Y, red, orange, yellow, G, green, Biv, B-I-V. So this is the what? This is the visible light spectrum. And I also sent you a picture of that. So let me show you that. So the visible spectrum is the spectrum that we can see with the human eye. And it begins in the what? Near the what? Infrared, 700. And it goes from about red, which is about 700 nanometers, all the way down to what? Violet, okay? Which is below 400 nanometers. So let's just do a couple of these problems real quickly so you can see what I mean when I say the speed of light is the speed of these. Let's go to the assignment that I gave you. Let me see. Chapter, I think it's here. Okay, so it says, what frequency corresponds to red light? So my equation says that wave speed, okay, that wave speed is equal to wave length times frequency. So this implies then that my frequency is equal to my wave speed times my wave length. So that means that because it is what? An electromagnetic wave, then I know that this speed is the speed of light, which is 3 times 10 to the 8th meters per what? Per second. And we just saw on that sheet that red light has a wavelength of about 700 nanometers. Nano means what? 10 to the minus 9 nanometers. So meters and meters will cancel out. Then I come over here and I say, okay, I've got minus 9, which is negative. When I bring it up, it's what? It's positive. So I got 8 and 9. That's 10 to the what? 17th. And I've got 3 divided by 700. And that's about what? 7 goes into 0.0. What is that? Okay. So we get 0.004. Okay, 0.00, say 0.0043. And then we got a per second, so that means we have what? We have hertz. Now, of course, this number has to be written in scientific notation. Let's see what I have here. Okay, 0.004. Okay, very good. All right. So let's write that number in scientific notation. So that means I've got to go how many times to the right? 1, 2, 3. So that gives me 4.3. Now look, this number got larger by what? 1, 2, 3. So this has to get smaller by 3. So I get 10 to the what? 14th. Okay, 10 to the 14th what? Hertz. Now, the next problem says this. The human eye is most sensitive to light with a frequency of about 5.5 times 10 to the 14th hertz, which is in the yellow-green region. You see, we're most sensitive, although it's what? 10 to the 14th, we can see that. It's most sensitive in the yellow-green region of the electromagnetic spectrum. So that problem kind of falls in place. And it says, how many wavelengths of this light can fit across the width of your thumb? So now I'm looking for what? I'm looking for wavelength. But my original equation is here, but now I'm looking for wavelength, okay, when I know what? The frequency. And the frequency is given. The wavelength is the speed of light. When I get that number, I will have so many what? Meters, because this is in what? Meters per second. But that number you're going to see is going to be, you're going to see it's going to be a very, 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 very small number. How do you know it's going to be a very, very small number? Because you have a very, very large number, 10 to the 14th, okay, in the what? In the denominator. When it comes up, it's going to be what? A negative number. So you got negative 14 and positive 8. It's going to tell you that number is going to be very, very small. So work on these problems here, and this is the basic equation for all of these. These problems are all so simple because they come straight from that one equation. And then these problems are just your thought problems. Now, I did not discuss with you this. So when you see a word like that, longitudinal, I want you to look it up. I want you to know, and I'm sure when you look in your textbook, it will discuss longitudinal as well as transverse waves. So that'll be something for you to work on your own. Okay, I only gave you 10 questions here, and I practically completed 9 and 10. So you actually only have about 8 to work on. I actually did 1 and 2 as well. Okay, this question is so easy. What is the wavelength of a wave with speed? See, this is not what? This is not a electromagnetic wave. This is just a longitudinal wave. And he gave you the wave speed and he gave you the period. So you can find what? The wavelength. All right. And on the other assignment, you have a few questions. And these all have to do with the ideal gas law. And up here, it has to do with moles and molecules. Okay. So with that being said, this is the last assignment. I want you to understand that the assignment that I've given you, all these assignments, I'm going to post the answer keys on the in Blackboard. I'm going to post them by chapter so that you can begin studying. Now, I'm going to go back through my notes, and everywhere I see where I have a key, I'm going to post it again, even if it's been posted before. And if I were you, I would take all these assignments now, and even take the ones I give you as the key, and start to work these problems. As you work the problems, refer to your final equation quiz, which now you will have in front of you, which will have all of your, all of your equations. Hold on. I don't know why my board is messing up so badly. Hold on. It thinks I want to share my hold on. Okay, I'm not sure why my I'm not sure why I'm not able to share the equation quiz, but you have it in front of you. So the point I was making is that you want to have your equation quiz filled out so that you can review all of your equations, all of your conversions, all of your constants, like the value of G. We've had several constants now that you need to have in front of you so that when you go through the homework, you will be able to work it. Okay, do we have any questions about anything? Okay, I made an error when it thinks I want to share my iPhone and I don't know how to get out of this. It's got me stuck and it's telling me to install something which I don't want to do. So let me just try to go back. Okay, so your assignment then is to work on the problems from chapter 14 and 16. I will be sharing the answer key in class tomorrow. I will only answer questions from the ones that you don't understand. In fact, that will be the case for all of the problems that I'm going to share the answer key for. So the answer keys will go up probably Friday for all the others. So your goal then is just to go through those, pick out a few, work them out, make sure that you can get the answers that is highlighted. Now, the last time I gave an exam, I noticed that many of you chose an answer that I didn't get. So we're going to discuss that problem. That's the one where we had, I think it was, we were looking for the new temperature. I can't remember what it was now. I think it was one of those heat exchange problems. But anyway, I'll find. I put a star by it when I did it. And I want to say this, that not always the answer that the author has highlighted is the correct answer. So if you have access to solutions somewhere other than working it out, just make sure you still work it out, just in case your answer is different from the author's answers or those who you may find on the internet. But I give you those very same questions for a reason, because I want you to be able to confirm your answer. If you weren't able to confirm it, you may not know if it's correct or not. I do the same thing myself. When I choose a problem, I choose the problems that the author has given the answer to, and I try to achieve that same answer. And sometimes it takes me more than one attempt to clarify that his answer is correct. So make sure that you're solving the problems yourself. That's what I want to emphasize, that you're actually going through and working the problems. So now we have 3 sessions to go through these chapters, a review. And I think I had said I wasn't going to review those first few chapters anymore because I've gone over those before the midterm. But if someone has questions on those, we will review. So the review will really start with chapter, I think it's chapter 5 or 6 that I'm going to do my more detailed review. So I've done 1 through 4 already, but I will go through with the equation quiz. Okay, if you don't have any questions, then go ahead and get started on your final equation quiz and the assignment I sent to you. And we will meet together again on tomorrow to begin our final exam review. Okay, any questions? If not, you can sign out as you exit. Okay, see you later, Lex. See you later, McCoy. See you later, Lanisha, Monier, Keston. See you later, Kayla. Okay.